to do such things as maintain firmware, moderate the current service provided by the ISP, allowing you to upgrade without having to have a whole technician come over and mess with your house, and provide troubleshooting information and feedback that can greatly facilitate speedy recoveries in the case of failure. To that end, our objective was to evaluate current implementations of the ACS that are out there. There have been several open source attempts to create such an implementation, but none of them as yet emerged as a clear top contender. To that end, we created this list of criteria. Based on these criteria alone, we were able to eliminate quite a few competitors. We had a few that simply created a socket. Claimed to be an ACS, only made a socket, failed to meet the other criteria. We had one that appeared to be an ACS, and as we built it, we discovered it was in fact a CPE, not an ACS. There was one that appeared to work but would not build. As we continued to work on it, we discovered that it failed to implement proper parsing and did not create a secure socket, merely a socket. In the end, this left us with two possible solutions, OpenACS and JCWMP server. Both of them have built and are currently working. However, OpenACS has been fully tested in the past, whereas JCWMP server is as yet untested. JCWMP server provides some excellent design choices that we had not previously observed. It is very modular and highly encapsulated, so it's much easier to extend and much easier to maintain than the OpenACS project, which is very cross-functional. It is our goal in the upcoming semester to fully test the current capabilities of both of our builds and to use the JCWMP server design characteristics as we extend the OpenACS project, which we do know has been tested. It is our goal by the end of our next semester to have shown some degree of functionality of our ACS on a small network. Thank you very much. Are there any questions?
What is your network set up right now?
At the moment, we have 5 not entirely networked machines running different distributions of Linux for cross-compatibility purposes. We will be bringing in consumer premises equipment provided by iPhotonix to use as our network base, which will be attaching our ACS to, ultimately to prove the functionality of the build.
By the end of semester 2, how do you already know what will define a successful project? Or what's the main thing that we judge?
At the moment, this will depend highly on what functionality we can prove our current builds have. If we can show that it implements completely the TR69 data model, we have 2 directions we can go. We can attempt to create a very, what's the word I'm looking for? Scalable, a very scalable solution, because all of these are currently very prototype proof of concept code. Or we can attempt to extend it using TR181, which adds wireless protocols and such on top of the ACS to allow it to extend its current functionalities. That will depend entirely on where iPhotonix intends for us to go with this final result.
Have you made any comments as to why there is only 2 of you
The core design of this project was to have an interface between engineering teams and computer science teams. Engineering because we will be having to deal with hardware issues as we merge together the networks. Computer science for the code analysis. We did in fact have a computer science team alongside us, but due to some unpleasant communication breakdowns in both directions, we wound up actually doing the same project twice. We did the same thing they're doing. We're both creating a technical document to show our final solution. It's the same final solution. paired programming within our own team. So all of these results were created collaboratively.